Today we have a fourth degree polynomial equation with only one known constant, namely the last term. Okay, now we also have this condition of multiplicity here, and let's just talk about how that imposes a little bit of structure here immediately. Y'all, a lot of you have heard of this notion of multiplicity. And this is what we mean. We have a root of multiplicity 3, and this is what it means right here. That root, x minus that root, quantity cubed, is part of the expansion. Okay, so 3 plus 1 equals 4. You see, there's an understood 1 right here. Understood 1 right here, the degree of this guy is 4, right? So you see, that's one of the rules. And it's some people think it's a technical definition, but it's a useful definition because the multiplicities sum up to the degree of the polynomial. Now, so again, this is exactly what it means for one of the roots to have a multiplicity of 3, x minus a quantity cubed times x minus b, where b is the other root, have this expansion. And again, this is equal. I should be saying that. I'm sorry. Let me call this p of x up here. We'll call this p of x. Okay, so this is p of x. And I think most people would assume that, but p of x is equal just to this expression by the given condition. Okay. Now, and again, it's kind of amazing that you don't even know these values except that they're rational numbers. You don't know these coefficients at all. All you know is the constant term, which turns out to be the product of all the roots. Okay. Now, of course, I left out a lot of the details. If you expand this out and multiply, you end up with this. And you see, you end up with this very nice term here, a cubed times b, which imposes a lot of structure. Okay. Again, this is the product of all of the roots. Okay. It's just that one of them is repeated 3 times. Okay. So this is very, very standard right here. You can see exactly what happened right here. This r has to equal to b plus 3a. You see there's minus signs in front of both of these when you expand this out. So all you literally have to do is equate r with b plus 3a. All right? And of course, 56 over 125, which is the only known constant term, is equal to this product a cubed times b. So you see, this turns into a nice counting problem, in my opinion. I'll be looking for anybody to see if I overlooked any of the possibilities. But I only found 3. Now, it turns out there's going to be 6, and I'll talk about that in a moment. But I do want to be real clear about what happened right here. Right here, a would be 1/5, right? And b would be 56, right? And then down here, a would be 2/5. And again, y'all, just going through all the possibilities that would accommodate the presence of a cubic term. So we got 2/5, and then b is equal to 7 here. And you know, it's not really necessary. We could answer the question right now without writing any of this down. Seriously, you could do the counting part of it, but I'm just being, I guess, thorough. So right here, a would be 1. And then b is 56 over 25. 56 over 125. Okay? You know, these are the only 3 possibilities that I can see. 3 possibilities for this to work and fit this a cubed b term. There's nothing else that's going to get it done, right? Because you know, it's just the nature of the laws of exponents and the nature of the problem that these are the only 3 solutions. I don't know if there's any formal underlying principle. These are just the only 3 that you can count. All right. Now, what was the question? How many values of r? Okay, how many values of r? Well, so far we would have 3 because for every one of these solutions, that will correspond to an R, right? I've given you 3 solutions in A and B. You substitute those in and you get 3 values of R, right? So far we have 3, but do note something that's very important right here is that minus A cubed, okay, that's supposed to be an A, folks, my deepest apologies, and then minus B times minus B. Of course, equals to A cubed B. And, you know, my entire life I've failed to learn how to write this A, or I refuse to, I guess. But this equality here, because if you cube a negative number, you just get the negative number back and then times the negative. This is flat out equal. So you see here's the 3 solutions, so there are 2 times 3 equals 6 values of B. Again, folks, I think this is kind of a fun combinatorics problem. Maybe you think it's trivial, but you're counting the number of solutions. And do note that just this right here, along with all of this, would have gotten you the answer. Writing down these answers was totally unnecessary, just trying to be a little clear about things. But you don't have to actually write the answers down. You know that there are 3 solutions exhibited by these 3 lines. And then this statement right here says you have to multiply by 2 to account for the negative values of B. So it's a combinatorics problem in its purest form where you didn't have to actually enumerate anything so much. Well, you enumerated, but there were no calculations, so to speak, is what I'm trying to say. But anyway, this is the answer. This is what I got. Now, y'all let me know. There's always somebody, a viewer, that seems to notice one additional answer that I may have missed. And I'm not overlooking that possibility. I spent quite a bit of time on this. I think I got it right. I think the answer is 6 values of B. And again, it's to me, it's kind of fascinating that something like this, or 6 values of R, right? God, what am I saying here? 6 values of R. Six values of R is what we're looking for, yes. How many possible values of R are we trying to find? Okay. All right, y'all, that is all. Again, let me hear from you if you see any flaws in my reasoning here. I think I got it right, but I've been wrong before. Okay, thanks for viewing.